Our topic is going to be on discussion about sulfur and halogens. Before we go, let us try to set our objectives right, as we always do. We are going to describe the preparation, properties, and uses of sulfur. Then do that for halogens and some compounds of halogen. We are going to be specific about some of the most commonest halogens like fluorine and chlorine. As a matter of introduction, sulfur. The occurrence of sulfur in nature is sometimes you have sulfur in elemental form, sulfur in the purest form of sulfur occurring in the earth as it is without combining with any other element. Sometimes we can have it like in sulfides, find a combined form with other metals like iron, like zinc, like lead and copper, sometimes like that. Sometimes we have it in a more complex form, like we have in solvents of some compounds like magnesium, like sodium, like calcium. So these are some of the ways we can find sulfur in the atmosphere. And of course, if our interest is going to get sulfur in elemental form, and we don't have it as elemental form in nature, so we can get any of the compounds and get our sulfur from it, as we're going to see later, inshallah. Another common compound of sulfur, apart from the sulfide of metal or the sulfate of metal, is hydrogen sulfide. Sometimes we have sulfur oxide. Although we have talked about sulfur oxide as when we were talking about oxygen, we're not going to talk about that one here now. So hydrogen sulfide is a product of natural gas and also occurs in volcanic gases. So when we have volcanic eruption, some of the gases that escape into the atmosphere, one of them is hydrogen sulfide. So we can get sulfur from here. That is another source of sulfur. And apart from that, in nature, in foods we eat, plants and animals, protein component, we have sulfur as one of the elements that is constituent of protein. So those are the ways we can, those are the sources of sulfur in nature. How do we prepare sulfur in the laboratory? As a chemist, we need to know how to prepare sulfur, and not only sulfur, like other non-metals we have talked about. The commonest method in the laboratory, and especially in the industry, is what is called flash process. This flash process was developed from the name of the scientist that discovered this method. The method is very, very simple. How they do it, we have 3 concentric tubes like this. When we have sulfur in nature, sulfur in the elemental form in the earth crust like that, we just need 3 concentric tubes. So this one, this and this. So when you have 3 concentric tubes, so we just make it in one of a chamber like this, put it into where we have our sulfur. Then we blow superheated water. The water that is heated to around 150 degrees Celsius, what is called superheated water. At that particular point in time, so water is going to exist as a vapor. So that vapor at that particular time, so depends on pressure, that is thermodynamics, depends on pressure. The pressure will now tell us what we are going to have. Is it superheated vapor or superheated subcooled vapor? So we are not interested in that anyway. Our own interest is we are going to heat water to 150 degrees Celsius. Then after heating the water to 150 degrees Celsius, it's going to have turned to vapor. That is taken. So we now pass this heat into the deposit of sulfur here. On getting contact with this sulfur, is going to melt it, because the melting point of sulfur is not up to 150 degrees. So after melting the sulfur, then we pass here into this place. Now this is compressed here that is going to pass from this inner tube. So when the here now meet this melted sulfur here, because of the density that's going to reduce when something is heated, so the sulfur that is heated now, the density will reduce, then it goes up. When liquid sulfur goes up, it's going to be in contact with this compressed air. Then the air is going to gain energy because the air that is compressed is cool, the sulfur is hot. When they come into contact, there's going to be exchange of heat. Then that sulfur will surpass it to the air. Then density of water and density of air will reduce further. Then here will move up. So when here is moving up like this, and here is going to go along with sulfur. So we're going to collect our sulfur from here. That is how this sulfur is being produced by frat process. Very, very good process, and no purification is required. The purity of sulfur got in this is 100% pure. Another one is when we can prepare, we can get sulfur from purification of hydrogen sulfide from natural gas and volcanic gases. That one is not, the amount of sulfur to get from here is not going to be much, because it's just a method of preparing sulfur. Another one is there are many forms at which sulfur exists. That is what is called allotropy. But at room temperature is stable, as I've discussed. It contains the 8-membered substance. Also, it makes it very strong non-metal. So some properties of sulfur. It's a non-metal. As such, we expect it to behave like a non-metal. How does a non-metal behave physically? We know non-metal should be at least, if it is colored, it must have a color. So in this case, sulfur is colored. It has its own color. It is solid. And there are some physical properties of metals that vary from each other. So from one another rather. So we are not interested in going into detail of that. So the chemical property is this: when we have a metal, metal is always reducing agent. So it oxidizes metals. So we give a variety of binary sulfide. Another one is, it depends on the environment to which sulfur present. If sulfur is present in a more oxidizing agent, then sulfur becomes reducing agent. So in a medium when sulfur finds itself to be a more oxidized material, the sulfur is going to act as an oxidizing agent. So the same thing as phosphorus, as we have discussed the other time. So let us go to the halogens. The halogens are the members of group 7 elements. As we call group 1 element the alkaline metal, we call group 2 the alkaline earth metal. So the same way we call group 7 element the halogens. They are very, very reactive. Like we have in group 1 elements that are reactive, little reactive, because they are metals. The same way in the realm of non-metals, group 7 elements are also reactive. As such, they don't occur freely in nature. Like we have sodium, potassium, that we don't have them freely in nature because of their high reactivity. The same thing here. So you have them in combination with other elements from compounds. They occur in seawater as halide, yes, because of the soft salt that is present in seawater. So you see chlorides of metals in seawater. Others can be in form of minerals, like calcium phosphate fluoride, calcium fluoride, like halide, like other sources of like sodium chloride, like potassium chloride, like magnesium chloride. There are many sources of halogens we have in nature. How do we prepare them? Each of them has its own preparatory method. Although we are not going to belabor ourselves with describing in detail how each of them is being prepared. So we just take maybe one or two that are common, like fluorine and fluorine, that are common now. We're just going to describe them and tell us the principle to which others are prepared. Fluorine, because of its high reactivity, so electrolysis is the best way to prepare it. So if you want to use electrolysis now to prepare fluorine, you can have a mixture of potassium hydrogen fluoride, then anhydrous hydrogen fluoride. So when we have anhydrous hydrogen fluoride and the mixture with this potassium hydrogen fluoride, we're going to serve as the electrolyte now. So when we have the electrolyte, so we just get inert electrolyte, graphite electrode now for anode and cathode. So when we have that, then we just set up our electrolytic cell. Then at the anode, we are going to have our fluorine because of the decomposition of electrolyte. So we are going to have our fluorine at the cathode. The two gases separated to prevent their explosive recombination. Yes, because when there is decomposition like this, it is better as fluorine is being separated from the cathode, hydrogen as the anode. So if we don't separate them, then there can be further recombination. Then it's going to render our process useless. For chlorine, commercial chlorine comes from electrolysis of sodium chloride. We have discussed that during sodium, discussion of under sodium. We can use electrolytic methods of some metals like potassium, like calcium, like magnesium. So when we have fused chloride for this, and use electrolysis to prepare them. So almost, if you see as if you try to think about what we're trying to say here, reactive halogens are mostly prepared from electrolysis. Another one is the chemical oxidation, and again is due to their reactive nature. So if they are not reactive, then we're not going to use all these methods to prepare them. So if you want to prepare others that are like iodine now, we cannot use electrolysis because iodine is not that reactive. Then we can use a displacement method. When we have iodide compound, you can use a more reactive method to displace that from it, so we can get our iodine. What are the properties of halogens? Like fluorine, and fluorine is pale yellow gas. Fluorine is greenish yellow. Bromine is reddish-brown, and iodine is grease black. Everybody has an iodine. In fact, it's being used in medical, in hospitals, at least to treat some sores in body. Bromine is only slightly soluble in water. That is one solubility, but miscible in all proportion in nonpolar surface, such as chloroform, like carbon tetrachloride, like carbon sulfide, forming solutions that vary from yellow to reddish brown. Yes, that is for bromine. Iodine is soluble in chloroform too, like bromine. It's soluble in carbon tetrachloride, like bromine, in carbon sulfide, like bromine, like any other carbons. What we're trying to say here is this: solubility in water is to a very limited extent, but in organic compounds they are very soluble. And then iodine dissolves only slightly in water, like other ones. It is like you see now, their solubility in water varies with the way they are on the table. Chlorine and fluorine are not really soluble in water, followed by bromine. Then iodine, that is very low in their group, dissolves in water, at least to a larger extent, although it's only slightly, but to a larger extent than others. In fact, it's being used in medical practice, as I've said earlier on. It is quite soluble in aqueous solution of iodide, sure, with which it forms brown solution. Fluorine does not get oxidized. It is because of its electronegative nature. It can only oxidize another substance. It can't get oxidized because it is the most electronegative element in nature that we have. How do we prepare halides? The first method and the simplest is the direct combination of the constituent element. If you want to prepare element chloride of element A now, just react A with a chlorine, A with a bromine, A with a fluorine. That is direct combination of elements. Then some metals that are higher than hydrogen can actually replace hydrogen and to form metal fluoride. When you have hydrogen halide, then you can have a metal to displace hydrogen. That is if the metal is above hydrogen electrochemical series. This method is not applicable to silver, to copper, and to to silver and copper. Even gold is not applicable to them. They are lower than hydrogen on the electrochemical series. Active representative metals also react with solution of hydrogen halide to form solution of metal halide. That is what we are trying to say. This one and this, they are not really different. They are not really different. But in this case, it's a gas, but this one is aqueous solution. You can use the same method to displace it in aqueous solution. So hydroxide, carbonate, and some other oxides, they react with solution of hydrogen halide to form solution of halide. So that is what we are trying to say here. You can have a carbonate, you can have hydroxide. So when you have a solution of an halide, then there can be reaction to form an halide. So this is titanium fluoride, this calcium chloride. You can use it to form anything you want to form. Then why are we even studying all these compounds? Number one is they are very, very useful. Even as you can see, we have been discussing their usefulness alongside them. That is those that are commonly used. In this case now, we have compounds of carbon, hydrogen, and fluorine that are replacing freon as refrigerant. Because I could remember when we were talking about oxygen, we talk about freon, that is the chlorofluorocarbons, and their effect on the depletion of ozone layers, which has directly affected our environment. So scientists are trying to replace the dangerous elements from this and replace them with some benign elements in case, to render our environment safer. Teflon, tetrafluorocarbon is a polymer that's composed of this monomer unit. So when we have this, that is tetra 1,2,1,2,2 tetrafluoroethane now. So when you have monomer of these, you can have them polymerized form to form Teflon. Teflon is very, very useful in the laboratory. You use it for tape, you use it to eat sometimes because of its very high melting point. Fluoride ion is added to water supplies and some toothpaste. Yeah, fluoride ion is very, very useful. In fact, fluoride ion is also useful. Use it to disinfect water. Chlorine is important to bleach wood pulp and cotton cloth. So there are many usefulness of all this. Bromine is also important in the production of certain dyes, and sodium, potassium bromide are also used in sedatives. Iodine is in aqueous solution with potassium iodide is an antiseptic. Yeah, that is medical science. Iodide salts are essential for proper functioning of the thyroid gland. That is also in chemical industry and the medical field. So that is what we have for today. So we are going to meet next time, but before we go, let us try to look at a review of what we have taught. Sulfur exists in nature as elemental deposit and also sulfides of some metals. It is prepared by frost process. It is also prepared by other methods, but frost process is the most industrially used because of the purity of the sulfur you get from it. Halogens are elements in group 7, that is their name. Then the most reactive ones are prepared from electrolytic oxidation. Representative halides are mostly prepared by a combination of the elements. Others are displacement reaction of halide in halide compounds. So thank you very much for listening. We are going to see next time on carbonate and non-metals. After this, then we're saying goodbye to non-metals, except if you want to deal with the chemistry of
carbon, that is towards organic chemistry. Thank you very much for listening. We're going to meet next time, inshallah. Thank you very much for listening. Don't forget to share our video.